Welcome to the second part of the lesson on section 3.2, the derivative as a function. In this lesson, you'll learn about graphing the derivative and finding functions to describe the derivative. Let's take a look at the derivative from a graphical perspective first. In our first example, consider the graphs of f, f prime, and f double prime shown. In part A, what does it mean for f prime to be positive? Remember that f prime represents the slopes of f at each x value. Positive slope would mean that f is increasing. By the same reasoning, if f prime is negative, that indicates that f is decreasing. A slope or derivative of 0 would mean that the graph must be flattening at that x value. So in this particular graph, f prime indicates that the slope of f should be positive everywhere except at x equals 3, where the slope is 0. Now if you focus on the graph of f, you can see that f really does increase everywhere, but appears to flatten a little at x equals 3. In part B, what does it mean for f prime to be increasing? Again, since f prime represents the slope of f, this must mean that the slope of f is increasing. And by the same reasoning, when f prime is decreasing, the slope of f is decreasing. If f prime were constant, then the slope of f would be constant. In other words, the graph of f would be linear. Let's compare those ideas to the graphs again. In this example, the graph of f prime is decreasing to the left of x equals 3, and notice that f double prime, which describes the slopes of f prime, is appropriately negative to the left of x equals 3. Notice that in this part of the graph of f, the slopes are positive and steep on the left, but become decreasingly positive as you approach x equals 3. Likewise, to the right of x equals 3, while f prime increases, the graph of f double prime is positive. In this part of the graph of f, the tangent lines would be shallow with positive slope and become steeper with positive slope as we continue to the right along the graph. In our second example, suppose f of x equals x squared plus 1. We'll estimate the slopes of various tangent lines and then use these estimates to graph the derivative. Let's start by graphing f of x. It should be a parabola with vertex 1 unit above the origin. Since the slopes of f are negative to the left of x equals 0 and positive to the right of x equals 0, you can imagine that the slope is 0 where x equals 0. Let's graph a point at 0, 0 on the other grid to show that x equals 0, the slope is 0. If we try to draw a tangent line at x equals 1, we can see from the grid that the line appears to have a rise of 2 while it has a run of 1. On the graph of the derivative, we can graph the point 1, 2 to show that when x equals 1, the slope of f is 2. Drawing a tangent line at x equals 2, the slope looks like it might be about 4. Graph 2, 4 to show that when x equals 2, the slope is 4. Because of the symmetry, we get the opposite slopes on the left side. The graph of the derivative of f appears to be a line. For example 3, we have two functions, f of x equals x squared plus x plus 2, and g of x equals x squared plus x plus 4. For part A, we need to find the derivative of f and the derivative of g. Notice that we're being asked to find the derivative in terms of x instead of at a particular value of x. This is different from the derivatives you found in the last lesson. Recall from the last lesson that we had two options for using a limit to calculate the derivative. One in which x approaches a specific value a, and one in which h represented the distance from a to a point near a. That first limit won't be very helpful to us in this example because we're not calculating the derivative at a specific value. To use that second limit definition to find f prime of x, let's simply substitute x's for the a's. So let's find f prime of x. Substituting for f of x plus h and f of x, we get the limit as h approaches 0 of x plus h squared plus x plus h plus 2 minus x squared plus x plus 2 all over h. After simplifying, you'll notice that the x squared, x, and 2 all cancel out, and we'll be able to divide by h to get 2x plus h plus 1. Substituting 0 for h, we get 2x plus 1. If you'd like to practice this, pause the video while you repeat this procedure to find g prime of x. You should have found that the derivative of g was also 2x plus 1. So the slopes are the same at each corresponding x value on each graph. Why does this happen? It's because the graphs of f and g are exactly the same shape. G is just the graph of f shifted up 2 units. If we were to use the same procedure as in example 2 to estimate slopes of tangent lines, we would find the same slopes at corresponding x values in each graph. In example 4, the graph of function f is shown. Where does f have a horizontal tangent? It looks like we could draw a horizontal line that skims the graph somewhere near x equals 0. In part b, where is the derivative positive? Or in other words, where is the slope of f positive? This would happen wherever f is increasing. F increases to the right of the point where it has the horizontal tangent. So this is where f prime is positive. F prime is negative where f is decreasing. In part C, where is f prime increasing? Or in other words, where is the slope of f increasing? This happens in the section of the graph highlighted in orange. Following this section from left to right, at first the slope is steep and negative. Then it increases to become shallower and thus less negative until the slope is 0. Continuing to the right along the orange, the slopes are shallow and positive, and then become steeper and more positive. F prime, or the slope of f, is decreasing in the other parts of the graph. Moving from left to right along the leftmost piece, the tangent lines would have negative slopes that are shallow at first and then steeper, causing the slopes to be negative numbers that decrease to even more negative numbers. On the rightmost piece of the graph, the tangent lines would have positive slopes that become shallower as you move to the right, causing the slopes to be larger positive numbers that decrease to smaller positive numbers. And then here's roughly what the graph of what we just said would look like. This concludes part 2 of section 3.2, the derivative as a function.